The so the program said that yesterday was logging to the system. Today would have been scripting and MPI, but since we finished most of the scripting yesterday, with that small example that we did to compute pi in parallel, I'll devote the whole day to MPI today. But before I do, maybe I can ask if anybody has any questions from yesterday, whether you tried to do any of that by yourselves later on after the sessions, and you have any questions, I can take them now. Okay. Right, so as I said, today we will be looking at an introduction to MPI, which stands for the so-called message passing interface. I should say, if you had either downloaded the slides or were looking at the web version of the slides yesterday, maybe you want to re-download them because something's been updated. So you should re-download those. Yeah. So right. So back to so this is just the same deck of slides that I had yesterday. It starts now from slide 23. If you want to follow along yourself. Okay. So MPI is sort of the de facto standard way to write parallel programs in the so-called distributed memory paradigm. So if you want to write your own application that can span more than one node, okay, so that you have this thing running and it can run beyond one node, so utilize more resources than what is available on a single node. Then the most common way to do this is using this message passing interface that we will look into today. So what we will look at is just some basics, what the basic idea is. And then we will talk about synchronization, so-called collective functions, and so-called point-to-point functions that you can use with MPI. Okay, just to get these things out of the way. So MPI is basically a library, okay? It's a collection of functions that allow you to do common tasks that are needed in order to program codes in parallel. So really it's a specification which defines what a valid MPI library should have in terms of the functions, what the names of the functions are, what the arguments are, and how they should work. The current specification and the current version is 4, which was released in June 9th, 2021. But I don't think this has been deployed right now on many systems. For most systems, you can reliably assume that you will have available MPI version 3.1. This doesn't really mean much to you because all the functions that we will see today, all the functionality is under version 3. So we won't be looking at anything which is in version 4 only. So MPI is a library specification, which means that it's sort of a specification. It's a document, right? It's a document that says these are the functions that MPI should implement, and then there are several implementations, like Open MPI, for example, is one implementation. So this is the actual code that implements the library, or MD API CH, and there are some vendor-specific ones like Interim. So in MPI, what the assumption is that you're running different processes, and each process has its own memory domain. Okay, so this is also something we basically assumed yesterday. It was true also for the example that we saw yesterday. So you run these different programs in parallel, like when we were calculating pi, and we had a variable like, you know, this n hit. If you remember, we had this variable that was remembering how many of these pairs of x and y's were in the shaded region, and we were incrementing it. So this n hit was a different variable for the different instances of the program that was running, right? It could have had a different value. And so this is what we mean here by a distributed memory paradigm. So each program runs in its own little memory domain. And even though we might name the variables the same, they are really different pieces of memory on the system, or on the systems if we're using more than one node. And they can have different values. So MPI, with this library that we're going to learn a few of the basics about how to use MPI, what it has functions that facilitate copying this data from one process to the other. Okay, so this copying can be to actually copy data between the different processes. It could be used if you want to synchronize the processes, etc. It might help to have a little picture about what we mean. So this is just the contrast between a shared memory paradigm and a distributed memory paradigm. So in a shared memory paradigm, you assume that all the processing units of the hardware that you're using, they have a common memory, like here. And examples are, you know, multi-core CPUs or threads of a GPU which share a common memory. Whereas in a distributed memory paradigm, you can have more than one of these nodes here. So here I've drawn 4 nodes. And so then you have 4 distinct, in this case, memories. And where in the shared memory paradigm, you can exchange data by just reading from the same memory, the same piece of data, like I show here. So core 0 here and core 1 can read the same piece of datum, the same data here, which I've drawn with red. In the distributed memory model, if you have cores here that want to communicate, you have to explicitly copy this data from one memory to the other via the network. And this is what MPI helps us do. It has functions that helps us copy data around from memory to memory. Right. So we saw this yesterday, but I'll repeat it again. So trivially, on Linux, you can do something like this, and then you just run multiple instances of the program identically over, for example, 3 nodes here, which I just named node 01, node 02, node 03. An MPI program is run in a similar way, and this is also similar to what we did yesterday with srun. So you type MPI run. If you want to specify the nodes, you can. and then you specify the name of the program, and then this program will be run on these three nodes, the nodes with the host names, node 01, node 02, node 03. So you just run three identical copies of the file. This program might be, this calculation pi. In practice, you don't need to specify the host names here because you use a job scheduler like we saw yesterday, where you just you reserve a set of nodes, and then the environment knows that you want to run this program on those nodes. We will be using MPI run. Just wanted to let you know that depending on the system, you might the right way to run an MPI program might be by using this MPI exec. So where I put MPI run here, you would use MPI exec. Or on some systems, the recommended way to do it is to use srun. In our example, we will be using MPI run. Okay, so an MPI program is a program like, the standard C program that you write, but just calls some MPI functions at some point in the program. So if we're using C, and this is what we're using, we will be using for the examples, there's a single header file with all function definitions, macros, and constants that you need to use. And so this is just, is that easy? No, it's not easy. But anyway, you include a single file MPI.h, and that has all the definitions. And in principle, when you compile this MPI program, then you need to link in, you need to do something like this, where you include the library, the path to the library, so that the functions are found. But thankfully, most of the times, almost all of the times, you don't need to do this stuff. You have a wrapper compiler that knows where all the libraries are. So you just type MPI-CC rather than CC and try to find where the libraries are installed on the system. You just type MPI-CC, and then that takes care of linking all the libraries in there. Okay, so all MPI functions begin with this MPI underscore prefix in C, and before any other MPI call, you need to call MPI init. Okay, this tells you that that you want to use MPI functions in what follows. This argc and argv are just the arguments to main that you usually see when you have a C program. These are the two variables the two arguments to the main function. So before the end of the program, you need to call MPI finalize. Even though you don't really need, I mean, the reason you need to call this is in case your program ends prematurely, right? This MPI finalizes to tell the runtime that now I've finished the program. And so don't use MPI finalize. The runtime might think that your program finished in error, right? So that's why you need to call this MPI finalize.
Excuse me. Are we supposed to write the program alongside what you're saying right now, or are we going to do it later?
No, we do this later.
Okay. So now we just watch.
Now you have to concentrate on the
Thank
slide. Okay, so this is the pattern that you usually use. Include MPI.h, then you have your main function with the two arguments. You call MPI init. You do something, call also some other MPI functions in here that I have three dots, and then you call MPI finalize before you return your main program. Okay, and that's sort of the template or skeleton of a typical MPI program. Okay, and just taking this a step further, two functions that you will, in addition to MPI init and MPI finalize, which are mandatory, two functions that you will almost always call in your programs is MPI com_size and MPI com_ran. These two functions, so the first one returns to you the number of all the parallel processes that are running in parallel. Okay, so you can determine the idea is that you should be able to compile your program in a way that does not assume how many processes will be used, right? Again, I'll bring back the example that we did yesterday with this pi calculation. So nowhere in the main program did we sort of make any assumptions of how many of these we would be running in parallel, right? So that's a good thing to be able to keep general when you write your parallel program. So you write it in a way so that you can run it with 2 processes or 8 processes, and either way, either you use 2 or 8. I mean, there is some logic inside your program that will take care of the parallelization depending on eventually how many processes you're actually going to run it on at a given instant. But that means that inside your program, you need a mechanism to sort of query how many processes you're actually running on. And this is this function here, MPI com_size, which takes 2 arguments. The first one is MPI com_world, and the second one is nproc. MPI com_world is a so-called communicator. Okay. Communicators in MPI are just groups of processes. All right. So you might want to run your program on some number of processes, I don't know, n, but then split the group up into subgroups, right? And the way you would do that is to use communicators. We won't be looking into this at all today, I mean, in this introduction, so you don't need to worry too much about what a communicator is, but it's, I need to talk about it because it's an argument to this function here. And all I will say about this is that there is just one communicator that's always available to you. It's the default communicator. And it's this MPI com_world variable, which just means all the processes in the program. Okay. So all the functions that we will see actually take as an argument a communicator, and we will always be using this MPI com_world as a communicator. So we talked about MPI com_size, which returns the number of processes that you're running on. And then MPI com_ran is the function that returns the ID of the process that is running. So if you have 8 of these, let's say you have 8 of these programs running in parallel, then nproc will have the value 8 after you call this function in your program. Rank, this variable rank, will have a different value on each of these 8 processes, right? On the first one, it'll have the value of 0. On the second one, it'll have the value of 1. And on the last one, it'll have the value of nproc -1, so it'll be 7. Okay, so this MPI function is used in order to differentiate between MPI processes. You can make no assumptions, no safe assumptions about the order in which. So I have a printf statement here, which prints the the rank and the number of processes. So again, if I run this on 8 processes, then what I should see is on one line, which will be 0, 8, another line, which will be 1, 8, another line, which will be 2, 8, etc., up to 7, 8. But the order in which I will see these print statements, I cannot make any assumptions on. Okay, so the order in which processes are given a rank and which one of those ranks is going to print first and which one is going to print last is completely random and arbitrary and not something you can know beforehand. Okay, so unless you do synchronization, which we will see later, unless you do some kind of synchronization, these processes are sort of running independently, and which one of the processes will hit first the printf statement is again up to chance. So for example, if I were to compile and run this program, I could see something like this. Okay, so I'm running 5 instances of this program that I showed you here. And so nproc will be 5 and all 5 of the processes that are running in parallel. But what differentiates them is this value of rank. And whether I see 3, 1, 2, 4, 0, or I see 1, 2, 3, 4, 0, or I see any other order, that's just completely up to chance. You can synchronize, though, between MPI processes using a so-called barrier. So this function here that I put MPI barrier causes a synchronization between the otherwise independently running process. So if you want this barrier to work, you need all processes to call it. And the semantics of this function is that any process that exits for any process to exit the barrier, first all other processes must have called this function. Okay. So if one of the processes is very fast in your program and comes to this barrier first, then they will sort of be stuck in the barrier until all the other processes come to this barrier. So if you want to, depict it, let's say you have, just for the purposes of demonstration here, you have 3 nodes where you're running your parallel program on, and somewhere along the code you have an MPI barrier, which I draw here with this dashed line. Then if you have a very fast node like node 2, it will call the MPI barrier, but it will just stay there until the other 2 guys enter the barrier. And now that all 3 of them have entered the barrier, then they can exit. And again, the order with which they go from there on is also not deterministic. But what is deterministic is that they all had to reach this dash line before they continue. Okay, so this is synchronization in MPI, and so I have some examples later, but first I will cover some basing functions. So I started with MPI barrier, which is the synchronization function. But the more interesting functions are those that actually do some communication between the processes. So the first set of such functions are so-called collective operations. They are called collective because all processes must be involved in the operation. This is in contrast to something we will see later, which are called point-to-point communication. So here are some examples of collective operations, and these are not the only collective operations that exist, but these are examples. These are also examples of collective operations that we will see in the exercises later. So so-called broadcast operation, which just means take a variable which is sitting on one node and send it to all the other processes so that they have a copy of it. If you want to distribute the elements of an array, which is an array which is on one process, you want to distribute it to the other processes, and this is called a scatter operation. And then sort of the inverse of a scatter operation is gather, which means if you have, if you have little arrays on the different processes and you want to collect them into a big array on one process, then you call a so-called gather operation. Another example is if you want to sum a variable over all processes, which is called a reduction operation. So just to depict some of these, so this represents a broadcast operation. So here I wrote broadcast a variable from one process to all processes, but you can equally broadcast a set of variables or an array of variables from one process. So here is process 0, which has this red array, which is 4 elements, and it can call a broadcast operation so that this, if you have, assuming that you have 3 processes in total, then this array, the values of this array gets copied to process 1 and process 2 after you call the broadcast operation. This could be useful, for example, if you have a process 0 reads a file and then wants the contents of the file to exist on all other processes. Yeah.
So in broadcast, does the variable remain on process 0 as well, or does it?
Yes.
Is it not there anymore?
Yes, yes. This does not destroy the variable on process 0. It just copies it. So this is not
Okay.
destructive.
Okay, I see. Thank you.
And this is true unless I specifically indicate so. So the same is true here. So process 0 in this case has this this array of 6 elements, for example, and what it wants to do is it wants to distribute the elements to the other 3 processes. So it wants itself, so it wants process 0 to keep the first 2, but then the other, the second 2 elements to go to process 1, and the third 2 elements to go to process 2. Then you would call a so-called scatter operation. So scatter, or same as distribute, right? Notice here that that process 0 is participating as a receiver as well as a sender in this scatter operation. That's just how the semantics of this scatter operation work. And then the same example for the gather operation, as I said, is basically the mirror of this. So the inverse of this, where you have, a small number of elements on each process, and what you want is to collect everything, so gather everything to a root process. Okay, so just to see what these functions would look like if you would actually implement them in code, the broadcast would look something like this, where the first element here is, the first argument is what you want to send, so the name of the array you want to send. So in this example, it was just array, right? Then the number of elements that are in this array that you want to send, and then the data type. So it is important to know whether you're sending integers, an array of integers, or an array of floating point numbers, or an array of characters, right? Because broadcast needs to be able to calculate the number of bytes that you want to send as sort of the product of the count and the data type. Root here says who holds is indicating which rank, which process is actually going to do the sending, whereas everybody else is going to be doing the receiving, right? So it doesn't necessarily need to be going from 0 to everybody. You could have a different root process. So for instance, rank 3 could send to everybody, in which case here you would put the value 3. And then again, you need the communicator, which, as I said, in these examples, we will use MPI from world everywhere. So here is an example of how you would call the broadcast in order to get the 4 elements double precision array named R, ARR, from 0 to everybody. If it's not an array, but it's just a scalar variable, then, you know, in C, you need to give a pointer to the variable. So you would add this ampersand in front so that you turn it into a pointer to the value of R, of this parity R. So as I said, you know, getting this MPI data type correctly here, so in this case it was double and in this case it was int, is important since MPI uses it to estimate the size and bytes that need to be transferred. And there's a full list of types available in MPI documentation. For example, if you hit this link, then you will see what the different data types that you can use in these functions are. Okay, these are the semantics of the scatter operation. Again, the scatter, I'll go back. So the scatter is this one here, where you're distributing the elements of an array to the other ranks that are participating. And so there's two things that, I mean, just looking at what we want to do here, then maybe it's obvious that what you need to specify is probably how many elements you want to send and how many elements you're going to receive on the other side in order for this scatter operation to work correctly, in addition to the actual arrays, the names of the arrays that you're going to send. So let's just, yeah. So send buffer is what the root process is going to send, and then send count is how many elements in total are going to be sent, right? Receive buffer is where you want the other ranks to put the data that will be sent to them, and receive count is how many elements are going to be in these little arrays that are going to end up in the different ranks. And indeed, you can actually have different data types, different send data type and different receive data type. We won't be looking into examples where these are different. It's a bit more advanced. So in our cases, if you're going to send an array, if you're going to scatter an array of double precision numbers, then you're going to also receive them on the other side as double precision numbers, okay? A root is the process that does the sending of the big array, and then the communication. So here's an example. You have a 12-element array on process 0, and assume you have 3 processes in total, including the root, okay? Like the picture we saw before. And so these 12 will go into 3 little arrays, which are 4 elements each, right? So this is going to be how you call this function. Again, you have double and double, of course, because it's going to be sent as a double and received as a double. You have the send array and the receive array on this. And that means that for process 0, so this big one, this needs only be defined on the process with rank 0 that is doing the sending. But this small one needs to be defined on all 3 processes, including the root process, because the root also participates in receiving the data. Here's another example. Let's say you have 4 elements here and you have 4 processes. So you want each element to go to a scalar variable. So not an, so on the other side where it's being received, you don't want this to be an array, but you want this to be a single scalar variable. Then the pattern you would use is this, where you have array here defined. You say 1 element to each process. And then on the other side, you're receiving it in this pointer to the element. And again, you have, you specify that you're just going to receive 1 double precision number. Okay, the gather operation now, which is the inverse, takes very similar arguments. It's just that, and now you have to remember that the receive buffer has to be the bigger one. That's
Maybe I have a question.
Yes.
So I'm just thinking that are you going to specify like which array is going to be scattered to a given process because, or it's going to do it randomly?
Didn't quite understand what you mean.
Okay, so let's say we have 4 arrays, array number 1 to 4 in the first process. So we want to scatter these to other 2 arrays. So is it going to scatter randomly, or you are supposed to specify which array from this first process that you are going to scatter to the other one?
Yeah, you would you need to explicitly put the name of the array here, right? So is that your question? I don't know.
So you specify the array that you are going to broadcast to another process, right?
Yeah.
Okay. Okay. So I was also thinking that what you are working on is an array of even numbers. So assume that you have, let's say, for example, you have 5 arrays in the first process and you want to broadcast into another 4 processes. So how is it going to be done? Because, or is it going to, normally, is it going to scatter equally, or you can specify also the number of arrays that you can scatter from the first array to the other one?
Okay. So so let me see if I can understand the question. So let's say this was 5 here, but I still have only four processes. That's the question. So this will still work the way I wrote it here. It's just that the last element does not go anywhere. Okay.
So it will remain in the first process.
Yes.
Okay.
If you want that to go somewhere, you do a second operation later that you send that last element somewhere. Okay. So indeed, if you, well, the other thing is we won't see this, but there is a function called scatter v. So it's scatter with a v at the end, which means that you can have variable sizes to be scattered to each rank. So if you use this function scatter v, which as I say again, we won't see this here today, but there is a function scatter v, which will allow you to send, I don't know, element 0 to rank 0, element 1 to rank 1, element 2 to rank 2, element 3 to rank 3, and then the last 2 elements to rank 5, for example. You can do something like this. Yeah. Okay, so the gather operation works very similarly. Here's an example. Let's say we have 3 elements of an array on 3 processes, and we want to collect them into the root process in a 9-element array. Then again, where it will be collected, this, which I call here array all, needs only be defined on the process with rank equal to 0. And then you call it in a very similar way as the scatter, just that the arguments are reversed. And similarly, if you want to gather scalar elements into an array, then again, you need to use a pointer, right, with this ampersand, a pointer to the scalar variable, because the call type here requires you to use pointer. Okay, and probably the last thing we will see is this reduction operation. So a reduction is defined like this, and as I said before, a reduction means that maybe it's easy to see this picture here. So you have, in this case, you have three processes: process 0, process 1, process 2, and each process has two elements of an array on each, right? So array 0, 1 on process 0, array 0, 1, of course, these can have different values, but they have the same name. And what you want to do is do some operation element-wise. So do some operation on the 0th element of each of these three, like maybe the operation is adding them, maybe the operation is multiplying them, subtracting them, doing a bitwise OR operation, I don't know, some operation on them, and then putting the results of that so-called reduction operation in the root process, whatever that is. Here it's 0, and doing the same for the secondary. So these are called reduction operations, and the call signature is this. So first you specify the array that you want to do that wants to be reduced, and then you specify the array where these data will land on the root process. You need to specify how many elements, of course, the data type, and now you have this MPI op, which is basically the operation you want to do. And as I said, this could be, for example, MPI sum means you want to sum the elements over the processes, and then root is the rank of the process where you want this to end up. Here's an example. You sum each element of a 3-element array over all processes. Then this would look like this, where you have the send array is the array where you want to sum the elements of, and the receive array is the array that will, end up having the result on root. You're specifying that these are double precision numbers, that the operation you want to do is the sum, and that you want the result to end up on rank 0. Similarly, if you have scalar variables, so this is not an array anymore, but it's just single scalar variables, then you have to use, ampersand to specify that this is a pointer to the variable var and a pointer to the variable sum. Okay, I write it here. So this, we talked about some notes on variants of the collectives so there are variants of these collectives that might be worth knowing about. So scatter V and gather V allow specifying, this was the question that we had, varying number of elements to be distributed or collected to or from the process pool, where you need to specify additional arguments that contain information about how the number of elements that you're going to send or receive varies. There's a so before we saw this reduction operation reduce, where we said that you do the reduction operation and the result ends up on process 0, but you can also have a so-called all reduce, which is the same as MPI reduce, but the result is then placed on all processes, rather than just a root process. This is equivalent to doing an MPI reduce and then a broadcast, right? Doing an MPI reduce so that the data lands on a root process. And then if you do a broadcast, then that will be broadcasted everywhere. Okay, and some operations, you can replace the send or the receive buffer with a special variable MPI in place. This instructs MPI to use the same buffer for receiving and sending. So an example of where you want to do this is, yeah, maybe you want to, where's the picture? Gather, for example. So maybe for this gather operation, you want to reuse the two first elements of this array here, so that you don't have two arrays, right? An S array and an R array. Then you could use the special variable MPI in place to say that for the root process, just overwrite whatever the send array is with the receive array. It's a bit of an edge case, so don't worry too much about it. It's just so that if you ever need to do this, you know that there's a way to do it. Go back here. Yeah, here's another example where if you want to do a reduction, for example, another example of using MPI reduce, then you want this to go into the same variable. So let me explain a bit better what I mean. So here you had var and you had sum, and you're going to do a reduction where the values of the variable named var is summed over all processes, and the result of the sum is going to be placed in the variable sum on the root process. So one of you might ask, but what if I just want to overwrite the same variable on the root process with the sum? So you would do it like this. So for every other process except from root will call the MPI reduce like this, where it doesn't specify here a receive buffer, it just specifies null. But the root process uses this special MPI in place variable, which means overwrite my input with the output. Okay. That's all I wanted to say about collectives. So we go now to point-to-point communication. So we said collectives are communications that require participation by all the ranks, but point-to-point communication is communication that involves transfer of data between just pairs of processes. Okay? So most common case is sending and receiving data. So the sender process issues a send operation to send some data to another process. The other process that expects to receive the data also needs to issue a receive operation. All of this is asynchronous, meaning that deadlocks can happen. Deadlocks is when, for example, one process wants to send to another process some data, but the other process that expects to receive it does not call the function to receive the data. Then this will result in blocking of the whole code. Okay, here's just a very trivial example. For example, you have process 0, 1, 2, and 3, 4 processes, and we want 0 to send an array to process 1, and we want 3 to send an array to 2, and these don't have to be the same sizes. Yeah. So this involves what we see here is 2 point-to-point communications, okay? The 1 point-to-point communication is between process 0 and 1, and we say that the other point-to-point communication is between process 2 and 3. So here are the send and receive functions and what they look like. So you specify the array you want to send, the number of elements, the data type, then this is the destination. So this is the rank where you want to send the data. And if you send multiple messages to the same destination, then you should differentiate them with an integer, which is a tag, okay? And here is the communicator. And then if you do an MPI send in order to send some data from one process to the other, then on the other process, you need to make sure that there's a matching receive in order to receive the data with those arguments. Right, so this n in MPI receive just determines the maximum number of elements that can be received. So you can send a bigger buffer, you can send more elements than you expect to receive on the other side. Okay. Okay, we said this, that the tag variable tags the message, so it needs to be matched between send and receive. You can use MPI any tag as the tag, which will just mean accept messages with any value of tag in the receive. You can also use MPI any source in the MPI receive, which means accept data from any rank, right? Any source. This status variable here at the end of the MPI receive is used to query the result of the receive, okay? But we will not be using it for anything useful here. So you can just replace it with this MPI status ignore, which just means I don't care about status. Don't bother, you know, don't return anything. Okay, here's a trivial example. Let's say you have process I and you want to send this array to process J. And the way that you would call the function is first you have an if statement saying, if I am rank I, then I call an MPI send. And if I am rank J, then I call the MPI receive. And here on rank I, I'm specifying that I want this to go to J. And on rank J, where I'm calling the receive, I'm specifying here that I want to receive this from rank I. Sometimes you want to do things like this, which is every process sends some data to another process. Okay, so they're all doing a communication, they're all senders and they're all receivers. So you do something like this. In that case, this what I wrote here will not work, right? So in this case, every rank is sending to the rank next to it some variable, and then there's an MPI receive called below, where you say receive data from the rank before me. The reason this will not work is because, so this will result in a deadlock, and the reason why is because the receive here can only be called if the send finishes. But the send will never finish because when each rank calls an MPI send, there is no receive on the other side, okay? So this will cause the program to block. So there's ways to do this. You can serialize the communication, which just means you can use a loop so that you're sure that, you know, first process I sends to process I+1, And after that completes, then you have to move on to the next process. But this this might be serializing communication that would be faster to do if you did it in parallel. And it's also, you know, error prone. So the one way to do this is to call this function called send receive, where you specify that in fact you want to do this sending and receiving in the same call. So here's how you would do it. You would say the send variable, the number of elements, the rank where you want it to go. The 0 here is the tag. And then again, these are the arguments of the receive side. Okay. So now you're specifying that I want to send and receive at the same time. There are additional variants to all these functions again. So there's so-called MPI I-send and MPI I-receive. So these are non-blocking variants where the I stands for immediate. These functions return immediately. That means the functions, they don't block waiting for the send or receive to complete. And then you use an MPI wait that queries whether this send or receive is finished. So here's a common pattern you can use. Use an MPI I-send. At the end, there's a variable called request. And now you can do some other stuff here while the message is being sent. And then at the end, when you want to ask the system whether the message has been sent, you call this MPI wait. Another variant is this send receive replace, which is like send receive that we saw in the previous slide, but where the send message and the receive message can be the same array. So the receive message overrides the send message in this MPI send receive. Okay, that's enough.
In the case of I send and I receive, is there any disadvantage? I mean, in order to use this instead of the previous one?
No, there's no disadvantage other than, I guess, more typing. There's more code to type because you need to call MPI I send. And somewhere you need an MPI receive, and then you have an MPI wait, where the other one is just a single function, right?
Okay.
That's the only, I think that's the only downside to using this pattern here.
Okay.
Okay, so was just as a bit of an introduction, but of course, all this stuff is very forgettable and hard to digest unless we do some exercises. So we'll take a short break now, and then we come back to see practically how we can use some of this stuff in some small example codes. So how long should we break for? Leo? Yeah. Okay. No, just give me okay. Yeah, so for the remainder of the day, we will look into these exercises, which are small and meant to demonstrate the functionality that I talked about in the first hour. So you can go ahead and do this now. Log into the system and copy all exercises from this folder to some local folder. Let me do this with you. So here's my it's my channel is not big enough. So I'm logged into the to the cyclone cluster, DB into NCP training, and yeah, I will copy this command, copy minus recurse. The minus R means recursively, so it copies everything underneath that folder. And so if you do this, then you should see 8 new folders, EX01, EX02, up to EX08. These are the 8 exercises that we will be looking at today. These exercises follow a common structure. So yesterday was helpful to familiarize us with logging into the cluster and navigating the file system, modifying files with Emacs. So now you can hopefully be able to modify files, compile, etc. And now you can use slurm and commands like sbatch and sq. In any case, each folder contains these 3 files where this dollar bracket n is just it's just a shorthand for either 0, 1, 0, 2, 0, 3, what, you know, the name of the exercise. So there's a make file. If you don't know what that is, I will say what that is in just a moment. There's a source code C file, which is always named x number.c, and there's a submit script. So one of these slurm scripts that we saw for the, you know, the last 10 minutes yesterday, which is basically the script that includes all those commands that we were using with srun. We put them in a script at the, you know, if you remember last time, yesterday. So this has been prepared for each of the exercises. So the workflow that you will follow will typically be, you need to modify the .c file as per the instructions that I will give you. You compile it by typing make. So the make file that I have included saves you the requirements to type MPI CC -o, name of the program, and then the name of the C file, right? So that is not necessary because I provided you with a make file, and so just by typing make, that should handle the compilation. So once you modify the program, as I said here in the first bullet, and compiled it, typing make, then you submit the job script with sbatch sub-number.sh, and then you look at the output, which will be found in this file here, ex number-output.txt. If you do everything correctly, the job should complete in less than a minute. So none of these scripts should run for longer than a minute. So if they do, you might have done something wrong. So the exercises are mostly complete, but they require some small modifications by you, which you should be able to reconstruct by looking at the slides that I presented so far with the arguments of the different functions. So the fact that the exercises are mostly complete means that you need to read and understand the code before you make the changes. And here's an overview of the 8 exercises. So in exercise 1, we demonstrate the use of these rank and size commands, which give you the ID of the process and the number of processes. In exercise 2, we demonstrate the barrier. In exercise 3, we demonstrate this broadcast operation. In exercise 4, you will get to use the scatter operation. In 5, you use also the gather operation. In 6, you will need to use a reduction. And in 7 and 8, so in 7, these are the point-to-point communications. So in 7, you will need to use send and receive, and in 8, you will need to use the send receive. All exercises have been tested with a specific module, so I'd encourage you now to load this module just to make sure that we're all using the same compiler. And yeah, make sure that nothing, some edge cases don't fail. Okay, so let's look exercise 1 we do together because just to see if we understand the workflow. So if you go to exercise 1 and you open it in a text editor of your choice, let me do it. Then let me do it with you, as I said. So I will navigate to EX01, this is the first exercise, and I will type Emacs, the C file. Well, let me first list all the files. So here are all the files. There's the 3 that I promised there would be: exercise 01.c, makefile, and sub01 for the SH, and I want you to open the C file. Emacs window 1.c. Okay, it is. And to do is what you need to change. So I would like you to put the right arguments here so that you get the rank and the number of processes in the variables nproc and rank. And so I remember that I have this on a slide somewhere up here. Let's go back, all the way back to see where we introduced these 2 functions. Right, here it is. So you need to call MPI from world and then nproc in the case of size, and MPI from world and rank in the case of rank. So let's do that. Delete this to do stuff. MPI from world, and this is nproc, and MPI from world, and this is rank. Control X, Control S to save. Select Control S. Okay. And to go back to where I was here on the slide. Okay. So once you've saved the file, then Control X, Control C if you're using Emacs to exit. So you're back at the command line, and make should compile the program now. If I set it up correctly, yes, there it is. You're just seeing the commands that are being called by this make. So now I should have an executable, EX01, and this now I cannot run like this. I need to, well, actually I can. Wasn't expecting that. Usually you can't run it like this, but anyway, it's useless to run it like this because we're just running one. It's not a parallel program if you run it like this. What we want to do is use sub01.sh to submit it. And let's just take a look what is in sub01.sh. So it's asking for 2 nodes, 8 processes in total, so 4 per node. And you know, it's specifying the reservation, it's loading the module here, It's saying that this should only take 1 minute, etc. Okay, so you don't need to modify anything in sub01.sh. I just opened it here in order to see what's inside. So again, the program that you needed to modify was just the .c file in order to add these two arguments here to com size and com rank. Yeah, I already said that. Okay, and so now sbatch sub01.sh will submit it. And this will indeed run very quickly, so you can see that I'm running here, but I probably won't be running for a long time. Yeah. So I typed SQ again, and the program has disappeared because it's finished. So before it was running, and now it's disappeared. Let's see, which one of you guys is none of you running. So probably just it happened fast also for you. Okay, and so now if you look at the contents of the output file, which you should have now in your directory, there should be an x01 output.txt. This was created by the job that you submitted. Then you should see nproc8, 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 etc. But rank should be unique, so you should have a different number on each line. Okay. And the last column is the host name. We saw how to do this before. So it seems like the system now decided to give us 7 processes on one node and 1 on an additional node on node 6. So we have 7 processes on node 5 and 1 on node 6. So note that this is what we said, that the order here is non-deterministic and random. So here, for example, 0, 1 are first, but then it goes 4, 5, 7, 3, 2, 6, just because these 8 processes are running in parallel, and which one actually hits the print statement first is just a matter of chance, right? Okay. Anybody need more time to run this, or? I'll take a. So you need to fill in the arguments here, and you can find that on the previous slide. Yeah, so you go all the way down. Yeah, so those are Yes, and now the debate so you see x of 1 by 3, so the P max is so you see So, just say again what the we'll proceed to the next exercise now, but just to repeat that what we did was, well, first we copied the.
Sorry, we can't hear you very clearly.
Okay, how about now?
Oh, yes, that's good.
Yeah, thanks. Sorry about that. We copied all the exercises, so this is just something we do once. We went into the first exercise, CDX01. Okay, now there are more files than we found the first time. What we want to do is we want to modify x01.c, oops, minus nw, x01.c. I'm just repeating what we had to do because there, I don't know, I think there was some confusion. We fill these in, right? Oops. Yeah, We compiled with make. Now we'll say there's nothing to be done for X1 because it's up to date. And then we submitted with SBatch. And we saw the output and X01 output took C. Okay. And right, so we noticed here that the output is random, as it should be, that's no surprise. If we want the print statements to be in order, then we can enforce it through a synchronization. And that is the topic of the second exercise. It's very similar to the first exercise. So now if you go one directory up, and then into X02, and let's look at ex02.c, then you see that this part is identical to before. Okay. But the print statement is in a for loop. So it goes from 0 to nproc. And then there's an if statement. If rank is I, then print the statement. And I am telling you that there is a place where you can put a barrier that will ensure that the order in which you get the print statements will be in the order of the ranks. So you can put a barrier in such a place to ensure that zero prints first, 1 prints second, 2 prints third, and then 3 comes under that. So there is a way to serialize these outputs, but you need to put a barrier somewhere in here. If you run it like this, the way it is without the barrier, then you get the same as before, right? Because there is no you cannot assume that the rank 0 is faster than rank 1, and so, for example, and so the print statement will be print first by rank 0 rather than rank 1. No. So these are all happening asynchronously. So even if you run it like this, then you will get a random order. But there is a place where you can put a barrier in order to get this in order. Right. Remember that the barrier only takes one argument, so it's MPI barrier, and then MPI world is how you should call it. So that's the function you need to write, but you need to put it somewhere in order for the print statements to appear in order. So why don't you try that for a few minutes? After you put the barrier, you need to save the file, exit, type make so that you compile it, and then submit it with the SBatch command, right? Same as before. You need to put the barrier somewhere in this loop. We will make the thing the print statement. Okay, so there's not a unique place to put the barrier. I mean, there's more than one ways you can do this. So for example, you can put it here. That should work. And if you put it after the if statement, that should work. So let's just see why it works. So all 8 processes are running this for loop, right? Some are faster than the others, so some ranks might be entering the for loop faster than other ranks. But what is guaranteed is that is that all ranks will move. If I have the barrier here, then it's guaranteed that all ranks will move to the next iteration only if they have all entered this barrier, right? So everybody starts off with I equals 0. And this statement here, if rank equals I, ensures that only rank 0 will print, and then they all block and wait for each other. So that ensures that the print statement for rank 0 will be first. When they all enter the barrier, then they can exit. They come around to increase the iterator to I equals 1. And then you see if rank equals 1 here, that means that only rank 1 will print the statement. You get a print statement for rank 1. And then they all enter the barrier and wait for each other. So that ensures that 1 will come after 0, etc., all the way around. Same will happen if you put the barrier up here, right? It won't work if you do something like if you put it in the if statement. So maybe it's worth explaining why it won't work if you put it in the if statement. So this means that only one rank will call the barrier at a time. So what you're doing is, okay, so let's say rank 3 is fastest. Well, if rank 3 is the fastest of all of them, then, you know, is super fast, let's say, then the rank 3 will still iterate this and will print the statement as soon as its iterator becomes 3, right? So it'll loop around twice, and then when I equals 3, it will print the statement, and then we'll enter the barrier and wait. And the same will happen for all the other ranks. So they will loop around until their turn comes to print, and that turn might be out of order. But in the end, they will all enter the barrier at different times. And then once they all enter the barrier, they come out and the program finishes. But this, because each process is entering the barrier at a different time, and in the if statement, it means that this is not causing any synchronization to happen. So let's see if I'm correct. Dispatch, stop 2, and yeah, so I have now the output. And indeed, you see that the ranks are printed in the correct order. Okay, this is not something you really want to do. It's mostly here to demonstrate the usage of the barrier, just to understand a bit how these processes run independently. So in general, you don't want to do things like this, where you have a for loop and you have a barrier, because that means that you start off with a parallel program, but then you're forcing a serialization. So we're not really doing a lot of computationally demanding stuff in the loop that we just serialized. But if we were, right, so this loop that we serialized is not doing anything that takes a lot of time. But if it did, then this barrier here would be a bad idea, because you would be basically serializing the different processes. And so you would not be getting any benefit from the parallelization, right? So this pattern here is just to demonstrate how to use the barrier, or at least to see, to understand a bit how the synchronization. Okay, so any questions before, do we break now? Yeah, okay, so any questions before we break for lunch? No. Okay. Then we're back.
90 minutes. That's
Okay.
a long break today. Well, 1:30. Okay? So please be on time. Thank you.
Thank you.